Excellent. All right. So, as Mike mentioned, here to talk to you today about some flash performance in our storage systems and sort of the problems we see, the solutions we see, and where we think the industry is going in this direction. As all of you, I'm sure, are probably painfully aware, is that there's a big performance disconnect in terms of what you can get out of commodity CPUs and what you can get out of your storage system. 10 years ago, we had 15K RPM drives doing about 300, 350 IOPS. Today, we have 15K RPM drives doing about the same number of IOPS. Maybe a microscopic improvement in performance, but not a whole lot. In that same period of time, CPU performance has, scaled by better than a factor of 10. So, if disk drives, laws of physics notwithstanding, scale at that same rate, we'd have 200,000 RPM drives delivering many thousands of IOPS at the same time. And, well, we just don't have those. So there's this increasing disconnect between what your commodity CPUs can deliver for you and what your I/O subsystem can supply it with. And there's really no good ways to plug that growing gap in an economic fashion. Just to give you an illustration, here's our standard, one of our 4-socket Intel-based Sun servers in a block diagram form. And plugged into that, you can have 8 or even 80 disks. So with 80 10K RPM 2.5-inch drives, you'd get about 16,000 IOPS. The HBA can deliver over 140,000 IOPS. So even if you have 80 drives hooked up to this, it's still a huge disconnect between what your CPUs can compute and chew on and what your drives can deliver. So there's this gap. You got to keep your CPUs fed and happy somehow. Otherwise, they're just burning dinosaurs for no real good reason. As Mike mentioned before, there are really two basic ways of solving this problem. One is to store as much of your working set as possible in DRAM, such that it's a very low latency, high bandwidth in terms of proximity to the compute. The other way is that if it exceeds what you can fit in memory, go put them out on high speed, high power, high RPM disk drives, short stroke them so you get ever more performance out of them and get your performance that way. And these are very traditional approaches. As Mike mentioned, this is what people have done in the storage industry for many, many years. Give you an example of this. Our pals over at IBM ran a TPC-C benchmark, and the system cost that they built their system up to deliver this performance was just under $3 million. What were the costs in that? Well, there were really two big ticket items, as Mike mentioned before. The DRAM, you can see here that they had 0.5 terabyte of DRAM built up using 8 gig DIMMs for just under $1 million. Now, 8 gig DIMMs, I'm sure you guys know, is not exactly the highest or the lowest dollar per gig in terms of DIMMs. The reason they went with 8 gig DIMMs was because apparently they had 64 memory slots and that's it. So how do you get the most memory? Well, you pay the extra bucks for the 8 gig DIMMs so that you can keep your CPUs fed with data as quickly as possible. The other thing is they had over 1,300 of these low-capacity, high-speed disk drives with a capacity of about 47 terabytes. The database, as Mike alluded to earlier, was only about 4 terabytes. So it's literally a 10x over provision in terms of capacity between the desired workload and what you have to buy in your spindles for performance. And again, that was a cost of over $1 million. So 74% of the cost of this system that they benchmarked was just to work around the problem of trying to keep your CPUs fed with data quickly enough to get your job done. So I'll give you a little bit of background in Flash and why we think it's so interesting is it's really reached an inflection point in these last few years that really is making a lot of things possible that weren't before. Back in 2004, on a dollar per gig basis, Flash was about the same price as DRAM. Right now, Flash, you got to check pretty much every week what the fraction is now of DRAM because it keeps changing. Earlier this summer, it was about 1/5 the price of DRAM. Now it's about 1/7 the price of DRAM. And those prices are just diverging. What Flash gives you is it gives you extremely low latency reads on the order of about 40 to 50 microseconds. Writes, however, are relatively slow. upwards of 100 microseconds. The interesting thing in both those regards are that the writes are driven, the latency of the writes are driven primarily by the technology of flash itself. These are NAND devices that we're talking about. And in NAND, when you have to program them, there's two steps you have to go through. First, you have to erase a block before you can program it. And then you go through the actual series of commands on the device to program your data into there. The erase cycle is what takes the bulk of time. The actual programming cycle is actually fairly quick. So the 200 microsecond on average writes are actually very divergent. That's talking just about the program side of it. The erase cycle can take up tens of milliseconds. So if you see a bunch of cheap SSDs out there, and for write performance, you see 10 to 50 millisecond writes, which we've actually observed. The reason is because the architecture in those are very unsophisticated, and they're actually erasing the block right there while you're waiting for a write, and it takes a huge amount of time. Also, due to the physics of these devices, they have a limited number of times that you can actually write and erase the actual cells in the flash memory chips themselves. There are two basic technologies. One is the multi-level per cell, which is what you see in all your consumer devices. Those store, as the name implies, you have a single cell laid out in silicon, and you store several different voltage levels. So if you want to store 2 bits per cell, those are 4 discrete voltage levels, and they're migrating to 8 voltage levels and 16 voltage levels, so you can get 3 and 4 bits per cell. As you can imagine, that has some serious implications because the voltage level that's stored in a cell is the same. It's based on the actual fabrication process. And that's the same for everybody. So if you have to discriminate between, 1.5 volts, 3/4 of a volt, half a volt, 1/4 volt, and 0 volts, that's actually sort of a fine discrimination. And as time goes on and you write and erase these, the ability of the cell to hold that much charge actually degrades over time, and the ability to discriminate between these 4 voltage levels actually gets worse over time. So on multi-level cell technology, you actually get an extremely limited number of write erase cycles, usually in the low hundreds of thousands. Compare that to the more expensive variety you get, which is the single level per cell, or SLC flash, which is what you typically find in enterprise class SSDs, where you only store a single bit per cell. So it's very easy to discriminate the 2 voltage levels. And because of that, you get, sometimes up to 1 million write erase cycles per cell while still maintaining the data integrity. So as with using these in SSDs, what we believe is that in the storage market, a few tweaks to these can really make them extraordinarily compelling. Just like disk drives, if you add a DRAM buffer in front of these in order to absorb writes, further hide the latency while you're in the background migrating them to the actual NAND cells, will actually help improve write latency. But however, that DRAM is now volatile, just like on your disk drives. So you really need a way to back that. So in the case of a power fail, you still have time to migrate the DRAM to the flash cells so that you have the data back when you resume your power. The way we're doing that in our designs is by using a supercapacitor. So the great things about flash is that they're extraordinarily low power compared to many other things in your storage system. So supercapacitors have enough charge to power these things for 5, 6, 7 seconds. And it only needs 1 or 2 seconds to finish the program of what's in DRAM to go into flash. So there's an over-provisioning there for safety. The other thing is that if you look at, say, like a SATA or SAS channel today, you get that 3 gigabits per second Mike was talking about. If you look at a single NAND device, typically you'll get about 30, 35 megabytes for a single chip. Not that great in terms of streaming performance. However, if behind a controller you were to have several of these cells, 8 or 10 of them, now you're talking, close to 300 megabytes a second with 10 flash cells there. So you have a degree of parallelism that allows you to actually saturate that 3 gigabit per second link now. So by scaling these things and packaging them right, you can actually create something very, very compelling that fits into your storage hierarchy really well. The complicated part of this is to do so intelligently requires a bit of work. What you'll see a lot of traditional storage vendors doing is say, well, flash, SSDs, they're great. Why don't you just use them in your system as tier 0? we'll let you or some combination of you and some administrative software decide what data to put there. It's just there for you to treat as another tier in your hierarchy. We, as Mike mentioned before, don't believe that's the best use of that technology, especially because it requires the single most expensive resource in your enterprise, which is administrator oversight. And that is something that doesn't come cheaply. Same slide that Mike mentioned before, and I'll just reiterate the point that the reason Flash is becoming, once again, ever more compelling to us and the industry as a whole is because it occupies that niche between DRAM and disk drives in both price and performance. So as you can imagine, not all SSDs are created equal. We did an announcement with Intel earlier this year. I was at the Shanghai Intel Developer Forum co-announcing this product that we've been working with Intel for a while on, which is their enterprise class SSDs. You've seen them announced now. And we benchmarked these compared to some other flash vendors whose name begins with S that we won't mention. And you can see that by integrating all these design concepts we were talking about before, which is the multiple flash cells for parallelism, the supercap-backed DRAM buffer for hiding latency, you can actually get a huge improvement in both read performance and write performance for sequential and random workloads by intelligently designing these devices. So what's our flash architecture? Well, we believe that the core design that I mentioned, many cells, reliability, and supercaps with DRAM are really a compelling design that fits across a whole bunch of form factors. Several different form factors that are interesting are not only the disk drive replacement form factors, which are in the 2.5-inch and 3.5-inch form factors, but a new form factor that we haven't talked much about, but we will later this year, called a mini DIMM, which basically looks like a DIMM sawed in half, that it looks to software just like a high-performance SSD, which allows you form factor-wise to put these in a bunch of locations that they otherwise might not fit. So we have two classes of devices, ones that are specifically optimized for read, others that are specifically optimized for write, which I'll talk more about in a minute here. And all of these are enterprise grade, that is, approaching a 3 to 5 year life cycle with 100% workload presented to them at all times. So the first one I'll talk about here is what we call Logzilla, or a write-based SSD. Where we use this in ZFS is in place of the traditional place you put NVRAM. We use it for an intent log, which is synchronous writes that have to be immediately acknowledged to the client. For those, we put them on these write-biased SSDs. And because these devices are getting written to all the time, that's their purpose in life, is we build these out of the single level per cell flash devices because you get higher performance for writes. You get more durability in terms of write erase cycles, which makes them ideal for, well, writing. The other thing is that unlike NVRAM, you can have these at arbitrary scale. 32 gig isn't enough, well, buy 10 of them and you have 320 gig. Because we're putting these out on the fabric rather than trying to find DIMM slots in the server to fit them, we can actually scale these arbitrarily, putting them out in a JBOD where it's cheap to scale as opposed to on your server motherboard where it's very expensive and difficult to scale. Because we're using supercapacitors, these devices have no battery issues for serviceability. One of the things that, again, you guys probably have to deal with all the time is that the batteries wear out after a while and don't maintain their charge, and you have to service them every couple years in order to make sure that when you need them, they'll still be reliable. So we're getting rid of that with supercaps. They charge within about 20 seconds after power on, and you're good to go. The first release that you'll see of these will support however many 24 gig or 32 or 64 gig write-biased SSDs you want to put in your system. Again, it depends on your workload and your budget, how many is right for you. The second kind of SSD is the read-biased, or we call them ReadZilla devices that we use these to cheaply, because they're a fraction of the cost of DRAM, extend the ZFS cache, or the ARC. So ZFS uses an algorithm called the adaptive replacement cache, which is an extension on some ideas presented by IBM back in FAST a number of years ago. And just like any file system, ZFS, manages buffers in DRAM and decides what to keep there and what not to keep there. What the ARC lets us do is do this slightly more intelligently and segregate the data into frequently used data and not frequently used data so that we can change our caching policy depending on what gives the best hit rate. And these are dynamically adjusted according to the workload over time such that you maintain the highest hit rate at all times. As the name implies, the level 2 ARC takes the idea of the ARC and adds a second tier to it with these read bias devices. So normally, obviously, you can't typically fit all of your working set in DRAM. So what you do is eventually your caching algorithm says, well, I'd love to keep it all. I can't. I got to throw some over my shoulder. If the application needs it again, off I go to disk. 4 to 5 milliseconds later, I have my data again. Well, that kind of sucks because 4 to 5 milliseconds with today's CPU speeds is a virtual forever. So what we do instead with the L2 ARC is that when we see that we have some memory or some data that we'd like to evict because there's not enough room for it, instead of throwing it over our shoulder never to be seen again, we actually pick it up and migrate it to this read-biased SSD, such that then the next time the application uses it, instead of being 4 to 6 milliseconds away, it's 50 microseconds away. So it's a much closer latency to the CPU than the disk drives would be. So effectively, you can think of this as an extension of DRAM for ZFS to extend the working set size. The first release is going to support just under 1 terabyte of these read-biased SSDs, and as we work on our data structures here a little bit, because you have to keep little notes to self in memory on where you put it out on the read-biased SSDs. As we shrink that, we'll be able to increase the capacity to several terabytes worth of this read cache, which is a lot more than most people can afford for DRAM, or even fit in their system for that matter. Any questions so far? Comments? No? Great. So that brings us to the slide Mike showed earlier, which is the hybrid storage pool. So with this technology, where you have DRAM providing its traditional role, you have write-biased flash absorbing writes at very low latency and high speed. You have read-biased flash extending DRAM at a much lower cost per gigabyte. And you have your SATA or large capacity SAS drives providing your bulk storage. You really get to have the best dollar per IOP because flash drives on a dollar per IOP basis are about a factor of 30 cheaper than the fastest disk drives out there. On a dollar per gig, obviously they're a lot more expensive. That's why your bulk storage is provided by the SATA drives. And once again, power per gig, SATA drives are far lower power or watts per gigabyte than your traditional high-speed SAS or fiber channel drives. And the flash power utilization compared to the rest of your system is really quite negligible. So this, with ZFS, understanding how to handle all of these pieces transparently and where to put what kind of data when, it allows you to literally get the best of all possible worlds here. So one of the things we did was we said, all right, this is a great story, let's actually try it out. So we took a random server and we had some amount of money that we decided to spend for storage, and we said, let's spend it 2 different ways. One is the traditional approach, where we'll buy high-speed 2.5-inch SAS drives, relatively low capacity. The other is, let's take those same dollars and spend them the way we suggest in this new model, which is to buy a write-biased SSD and a read-biased SSD, along with a bunch of low-power, low RPM, high-capacity SATA drives. Then we'll take FileBench and we'll run a few benchmarks across it and see what we get. And the results were kind of interesting. So in terms of cost, they were within, a few dollars of each other. The hybrid storage pool delivered slightly more write IOPS than the traditional one did, and over a factor of 3 better on the read IOPS. The reason the write IOPS were only slightly faster is because eventually your backing store has to be able to keep up with whatever incoming workload you have. And so that means everything eventually has to go to disk. And that's sort of the delta there. We saved a lot on latency. The bandwidth to the disks, roughly the same. So the performance only wound up being marginally better. The other interesting thing is for your same dollars, not only do you get better performance, but you also get 2x the raw capacity because we're using the 400 gig high capacity drives rather than the 146 gig high performance drives. And your power utilization for the storage part of your subsystem goes down by almost a factor of 5. So once again, you really do get the best of all possible worlds with utilizing this technology. So I'll give you a little code diagram of ZFS here. One of the reasons that we're able to take advantage of these sorts of technologies relatively quickly is because when we were designing ZFS, one of the things we knew is that file systems don't have a lifespan measured in years. It's typically measured in decades. If you look at any file system in wide use today, when was the core of it designed? You know, ext traces its roots to UFS, which traces its roots to the Berkeley fast file system, which is, you know, early 80s in Berkeley. You know, VXFS, same idea. You know, it was developed in the early 90s. Waffle, early 90s. So all of these technologies literally last for decades. So in the design of ZFS, one thing that we knew is whatever we had in mind today certainly would be wrong 20 years from now. And we wanted to design the code and be very aggressive about this in such a way that we could redesign parts of it to adapt to whatever the technology trends happen to do to us without changing the rest of the code. So these two innovations that we talked to you about today, which is the ReadZilla devices that we use for L2ARC and the WriteZilla devices we use for the log device, really required very minor modifications to ZFS. The WriteZilla stuff required us to modify the ZIL or the ZFS intent log to know about a special device that it could use that was high performance and low latency. And the other thing is we modified the ARC such that it knew that rather evicting stuff into the bit bucket, it could evict them instead to these read biased SSDs, again, so that when it needed to get them later, it would have a much lower latency place to get them from. And just to give you an idea is that there are many classes of drives at many different points in both form factor and price and bandwidth and capacity that'll be coming out over the next year or so. And one of the things that you'll probably see from us in the future is you've seen us work with Samsung to tweak their flash process technology to give more higher reliability and better performance for us. And we are working very closely, you know, with Intel, and we've announced our relationship with Samsung. There are 2 or 3 other vendors that we're working very closely with, again, to lead the innovation in this part of the storage industry. Any questions, comments?
Hello? Okay. Let me just read this. So the question is, what about the class of flash devices connected directly instead of via SSD? Do you sort of feel that SSDs are the main sort of interface that people are going to use to attach flash to their systems?
So yeah, there are really 2 ways you can go about it. One of which is we're also working with Intel very closely on the new generation of the protocol. Sort of like they had the host controller interface that they developed that was their standardized way for the OS to talk to a disk controller that then talk to the drives. They're doing the same thing for non-volatile devices, flash being an instance of those, phase change memory being another one coming up. So that will be one way of doing it, but one of the problems with that approach is that, again, you're sort of limited to what you can put on your motherboard, what you can put in your box, whether it's over PCI on some custom ASIC or FPGA that you made that distributes stuff to flash, or whether it's on the motherboard in some other form. You're really limited to physically what you can put in there next to your CPUs. The advantage to SSDs talking over a SAS or SATA protocol is that they're arbitrarily scalable. You can have as many of them as your pocketbook, you know, can afford. And so far, what we've noticed is that the latency, while there is a delta in latency between putting them extraordinarily close to the CPU or out on the storage device, it's not like a factor of 2, it's a factor of percentages. So there's the scalability we feel outweighs the slight delta in performance that we get by moving close to the CPU. But our future servers will have some closer to the CPU just because it's a convenient place to put them. Any other questions? Well, that was easy. Oh, Ben, all right.
I got to make your life difficult.
Hello.
So one of the things when you look at things like level 2 caching and things like that is trying to gauge at what point I need it. So with ZFS Arc, would it be correct to say that if I wanted to determine whether or not my existing system actually could benefit from L2 Arc, would be looking at the ghost hit rates, particularly on MFU?
Yep, that's one way of doing it. And as you saw from the slide that Mike presented earlier, that's one of the areas that we're focusing on our future storage servers is the observability of exactly this. Knowing how much of my memory is dedicated to cache, how big is the working side, what's my eviction rate out of the Arc, and things like that. And again, there's generation 1, it gives you the raw statistics, so you as an administrator can sort of scratch your head and say, well, I think I could add some L2 Arc. In the future, we're going to have slightly higher level metrics around that, such that we could say, oh, your working set appears to be on the order of this size. Again, that would lead you to decide how much of your L2 Arc to purchase.
And there's been discussion about some of the tunables within ZFS eventually being removed. With L2 Arc being in there, would that suggest that the ability to limit arc size is probably going to be there permanently?
Probably, but again, the reason those tunables are in there is because we couldn't figure out a way to have a heuristic that worked across everybody's workload to always give you the right answer. So in those cases, until we figure out an algorithm that does that, the tunables are probably going to stay.
Okay.
For your performance analysis, performance management, call it whatever you will, has any consideration been given? So you've got the modifications for the Arc side and the ZIL side to exploit the flash, and then it sounds like you're going to use dtrace to assure some sort of quality of service at a higher level for like NFS and CIFS. And I was just wondering if there's any consideration been given to looking at the different options available in ZFS, whether it's compression on or off, or the checksumming capabilities where you have I think it's 3 options, 3 different ways you can checksum, and how that might be hooking into your infrastructure going forward.
Yep, those are also things that are observable through dtrace and through the analytics that Mike was talking about earlier, is how much of your CPU is being utilized as data is streamed in and out. And the checksum, compression, and in the future encryption are actually 3 areas that we've been working with CPU designers on to come up with instruction set extensions that actually allow you to do these sort of general operations in a much more high performance situation. Because, for example, just about every compression algorithm on the market today uses some variant of the Lempel-Ziv algorithm. So CPU vendors in the future are talking about, well, what happens if we add instructions that actually accelerate the string scanning and comparison that you do as part of the dictionary building in Lempel-Ziv. Same thing for encryption. You already see people adding instructions to their CPU to do cryptographic hashing and encryption. And so we are planning on taking advantage of those extensions as they become available in performance to help just the situation as a whole, in addition to providing the observability to figure out how much of my CPU is being dedicated to this, and am I at my limits for CPU or not.
I have different kind of the question because here is a analysis about the performance of the solid state disk based on the flash memories. But as far as I know, here is also the limitation of the write cycles in the lifetime of the flash disks. It's 10 to 5 to 10 to 6 write operations available. So how you think you can deal with it? Because in a performance of the current flash disks, such number of the write cycles can be wasted in several seconds.
Yes. So one of the things that we've done in our design with Intel is that we've worked very hard on the expected life cycle and performance of the write bias devices, because as you point out, that is their purpose to get written to, and that eats up those cycles quite quickly. So what we do is we figure out how many write ops can the device consume, and then given the capacity of the device, what does that mean in terms of reliability? If, say, it supports on average 500,000 write erase cycles before it can no longer reliably store your data, what we do then is we say, all right, at this many 8K IOs per second, how long does it take us to exhaust the write erase capabilities of this? That combined with a advanced wear leveling that Intel does in the firmware of their controller, such that even static data periodically gets picked up and moved so that all cells on the device are worn evenly. What we do is we actually over-provision a little bit the capacity. So for example, if you have 32 gig raw of flash cells, maybe we only allow 24 gig of them to be utilized at any given time. That allows us to have better performance because it allows us to do sort of an erase ahead kind of algorithm where we have a whole bunch of cells sitting around erased waiting to be programmed, so you don't have to wait on them when your writes come in. The other thing is it allows us to do 8 gig worth of retires of worn out cells before the device runs out of capacity. The nice thing about this is that the firmware on all these devices that we're working on monitors the reliability because each flash block has a number of ECC bits associated with it. And it monitors how many of these ECC bits are needed to repair any worn out data. And as those number of bits increases, it basically says, oh, cell's worn out. So what it can do is it can actually retire blocks and reduce the capacity of the drives. The nice thing about the particular architecture we have in ZFS is both for the intent log and for the level 2 ARC, if the capacity of those devices decreases, functionality is still preserved, just at perhaps a slightly reduced impact on performance. So we have sort of a confluence of things that help us mitigate the wearing out of the flash cells. Does that answer your question? Close enough? All right.